Let's look at this example. Determine if this set is linearly independent, well, if the vectors are linearly independent in R3. Now, clearly, we can see that this set of vectors cannot span all of R3, right? So you have to have the same number of vectors as the degree, or as the as n to to span them. But are they linearly independent, or are they basically the same line? Right. So they represent basically a vector, right? So it's either going to be two of them that are linearly independent like that, or it'll essentially be the same vector, or just a vector that's parallel of some sort or opposite direction. So this part we've done a number of times now. What you're trying to see is if the only way to get this to be 0 is if all the r's are 0. So we say R1, R2 set equal to 0, and you get these two, you get this system. So when you do that, so R1, R2 both not 0. So that's the question, right? That's what we're really trying to find out. So we're setting up an equation, and you really only have two variables, right? It's two variables, but we end up with three equations because you have the three components, 1, 2, 3, for the vectors. So that's what you're looking at here. So you have your vector. So this is V1. Let's change the color on that. So you have V1 and V2. But then when you multiply this out, you get this, okay, for each component. And then when you add those two vectors, you're just adding the components. Here's your R1 plus R2. Here's R1 plus the 2R, right? And then you get this, you get these. And so is this equal to 0 or 0, 0, 0? So you're setting each one of these components equaling 0. And that's so you get that system. But this system has too many equations, but you still solve it the same way. Okay, so here's your 1, 1, negative 1, 1, 2, negative 2, and then you row reduce it. Okay, so you row reduce. And let me erase this. This was in here to show you stuff, but this is what I was looking at. Oops, erased it too far. Okay. So what you end up having then is these two pivots, which represent these two vectors. And so that's good enough. Because even though this zeroes out, that's kind of okay because because we only had two vectors to start with. So these two vectors, that represents this vector, V1, and then this represents the second vector. Those are linearly independent. So V1 and V2 are linearly independent. There's pivots in each of those two. This doesn't matter because you're only talking about those two vectors. So we've done that part before. Now what we want to do is enlarge the set of vectors so that you have a set that spans all of R3, or that becomes a basis, not just spans, it becomes a basis for R3. So that's what I want to show you. So now enlarge W to become a basis for R3. Okay, so let's let v1 be this vector. I already labeled it up there, but we're kind of relabeling it for this question. And v2 be 1, 2, -2. We know that this set of vectors, e1, e2, e3, is a set that spans R3, or a spanning set for R3. So what you do is you basically create this big matrix with these vectors and all of these vectors as column vectors, and then you row reduce. And then you see which ones zero out. It's kind of cool how it works. Although I wouldn't worry about this like a lot. You'll be able to just follow along if ever asked to do it. Right, so you write R3 would equal the span of all of those vectors, v1, v2, e1, e2, e3. Do you see how that has to be true? Right? We know e1, e2, that's ijk, right? That's basically ijk, but we're going to use the notation e. So this has too many vectors in it, but it's still, the span will still equal R3. Every vector in here can be written as these vectors, and all of these vectors, linear combinations, will create all of these vectors. So apply the same technique and keep v1 and v2 in the first two columns. And we'll just write it down. All right, so you write 1, 1, -1, 1, 2, -2, and then now go ahead and write 1, 0, 0, 0, 1, 0, 0, 0, 1. Like that. And then you row reduce to see what happens. All right, so when you row reduce, you'll get 1, 0, 2, 0, 1, 0, 1, -1, 0, -1, 0, 0, 0, 1, 1. And that's just by the calculator. So we look for the pivots, basically, right? So you go down here, that's one, next one over, that's one. So these two are linearly independent like we thought. But this is not a pivot, so you don't use this one. You go to the next one that has the pivot, which is this one. So you skip over this guy and go to this guy. So that would be E1, that would be E2. All right, so I'll show that to you again. Okay, so you have these two represent these. And that was V1, V2. This was E1, E2, E3. And so we use this vector. I guess that would be E3, because it is E3. They kind of switched, of course, but that's okay. So the point is V1, V2, and this vector here spans all of R3 and is a basis. That's actually E3. All right, so this set here, oh, I can't stand when I do that. This set here is a basis for R3. Okay. Next example. I have it copied down here. Let's take a look at this one. So this example, let V1, V2, V3 be an Rn. Prove that W1 equal to this, W2 equal to this, and W3 equal to this are dependent. So basically what you're saying then is notice that this is not any specific dimension. I'm saying it's an Rn, and I'm saying these three vectors are here. But then I'm creating these three other vectors, which these, of course, are linear combinations of those other vectors. So now we're going to show that those are dependent. So this is how you want to go about it. Let's write this. Let's say suppose R1 W1 plus R2 W2 plus R3 W3 is equal to 0. All right, now find the R sub i's that would give you 0. So substitute now your substitute here will be that, and then this guy will be this, and then this guy will be this. Substitute for all of those, and you get R1 times your W1, 2V1 plus 3V2, and then R2 is W2, which is V2 minus 2V3, and then R3 is W3, which is negative V1 minus 3V3. And that's set equal to 0. So now expand and collect. So now expand and collect where the R sub i's are coefficients. So right now, of V1, V2, I should say. They are already coefficients, right? I meant, so of V1, V2, V3. That's what we want to do. So I'm not going to show that step, but you basically are just expanding this out and collecting all your V1s together, all your V2s together, and your V3s together. So it'll look like this. So then we have 2R1 minus R3, V1 plus 3R1 plus R3, V2 plus negative 2 R2 minus 3R3, V3 equal to the 0 vector. So now you're just setting each one of those equal to 0. So you want to, so we're showing that basically what values of R would make this 0. So we know it's going to be dependent if there exists R1, R2, and R3 that gets this to be 0. Remember, they're linearly independent if the only way to get 0 is if all of these are 0. So we're basically showing that that's not the case. So I wrote this down. I don't know if you're going to like this, but show there exists R sub i's such that R sub I are not all 0. All right, so we want to set the coefficients equal to 0 and solve the system. So when you do that, you get 2 or 1, and I went ahead and wrote this out, expanded kind of like this, and then 3R1 plus R2, and then negative 2R2 minus 3R3. So write this down in a matrix and row reduce. And what you'll see is you get a row to 0 out. If you got the identity matrix, then you would be showing that they are linearly independent, but you don't. So you get 1 row to 0 out, and that means R3 will be anything, and so there exists a non-trivial solution. When you row reduce, you get 1, 0, negative a half, 0, 0, 1, 3 half, 0, and then you get this last row to 0 out. Okay, so what that tells me then is that R3 can be anything, just like we did before. Therefore, there exists a non-trivial solution. There's like an infinite number of them, but still. And the vectors are linearly independent. So, and the vectors are linearly dependent. Did I say independent? They're dependent if you find a non-trivial solution. Okay. We have another one. So last one it will do before we go on is this one. Okay, so, oops. Which one was which? So that shouldn't be the same one. That's clearly the same one, which isn't what I wanted. So we're not doing that one. All right, so let me erase that. I must have copied the same one over. Well, that's weird. Okay, well, I can copy it. So let's just look at this one, and we'll just look at the whole thing. All right, so this is 33. So we'll just go through it then. How about that? And wrap this up. So number 33, find all scalars S, if any exist, such that these vectors are linearly independent. So you set it up the same way, R1, R2, R3, just like that, and you set it equal to the 0 vector. And so you expand and get a system. So the question is, are there values of S such that this system has a non-trivial solution? So you're still looking for that. If you show that the only way to get 0 is if all of the R's are 0, then it is non-trivial. So you set it up and solve this system just like everything else. And so the difficult part is you have a variable in here, S, and negative S. And so that makes it to where you, unless you have a little more powerful calculator, you will not be able to solve it using row reduction. So you got to do it by hand. I haven't tried it, but I'm sure a computer algebra system, a CAS system, would probably be able to do it. But even that, I don't know these days. But that's not the point. The point is just zero this out and zero this out. And then see if you can get the next one to zero out. So you set this up and you just subtract the first two and you get 0. Do the same thing here. And then, excuse me, and then you get these to be 1. Okay, and then eventually you can get this to 0 out. Okay, so you can play with that to see how I got that. If this zeroes out, what does that tell you? This tells you that R3 can be anything. It has an infinite number of solutions because R3 is any value. Therefore, it's a non-trivial solution. Therefore, it's dependent regardless of S. There are no S values that'll give you a linearly independent vectors. Okay, so therefore, the vectors are linearly dependent for any S, for all S. 2.2 is next, going on to the rank of a matrix.